Hi everyone, I wanted to go over with you the structure and function of a voltaic cell. So this section on electrochemistry is the second half of this unit. So the first part, the redox part, which is explaining to you what a redox reaction is, the transfer of electrons from the substance being oxidized to the substance being reduced. This portion, electrochemistry, puts these reactions to work because it's all well and good, like, oh yeah, electrons are moving, you can't really... you could see it if I dropped a piece of aluminum foil into a solution of copper sulfate, you would see copper metal forming, and that's a redox reaction. Combustion is a redox reaction. Obviously, that could be put to use for us. But your regular everyday redox reactions can be put to use through the process called electrochemistry. So electrochemistry ties together the concept of electrons that are coming from the chemical reactions. So I'm going to go over the first type of electrochemical cell with you now. This is called a voltaic cell, which was introduced in that short Professor Dave video. If you look in the links section in the content library of this chapter, I added several new videos that I found that are really good on explaining this a little differently with some more diagrams. It's really hard to do this through video. I'm going to do my best, but if you want to check out those other ones, they really provide a nice outline of these concepts as well. So look, there's different kinds of cells. Look how witty I am. Ha 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 ha. So the one that we're looking at is going to be this kind. Look at that super fun one. Okay, so there are two different types of electrochemical cells that are practical uses for redox reactions. So both types of electrochemical cells involve chemical reactions and the flow of electrons. So the type we're going to look at today is called a voltaic cell. This is notes part 2, by the way. And the other type is an electrolytic cell, which will be in the other video. Okay, so they both involve redox reactions, right? Reaction that has the flow of electrons, but we're just going to focus on this voltaic cell. Another word for this is galvanic cell. So for a voltaic cell, it generates electricity as a result of a redox reaction. And it's going to be spontaneous, meaning as soon as you hook this thing up and you put the pieces together, the electrons are going to flow. You're going to get a voltage reading. So this reaction causes the flow of electrons through a redox reaction. Therefore, electricity is produced. Electricity is the flow of electrons. We're just putting it through a circuit. So I'm going to draw the parts of a voltaic cell, just bask in my artistic ability here. And then we're going to go through what each of the parts are. Okay, so the first thing we need, and I'm going to kind of draw and label this simultaneously. You'll see the next couple of slides have the labels as well. So we're going to have two containers. This is going to be a half cell, and this is going to be a half cell. So it's just going to be a beaker, okay, two different beakers. The purpose of having the half cells, one is going to be for oxidation, one is going to be for reduction. So we're taking that redox concept and we're just separating the two components. You do need to have the two beakers connected in some way. So in between these two beakers, we're going to have kind of like an arch, and this is going to be called a salt bridge. Now, a salt bridge could be a couple different things. You could have just a piece of filter paper that has been soaked in like a salt solution, like just regular sodium chloride solution or potassium nitrate solution, and kind of draped into both sides. What I have in the lab is I have glass tubes. They're called U-tubes. And I would fill the U-tube with the salt solution and then stick like pieces of just regular sponges in each side. So the sponges prevent the solution from leaking out, but it does allow ions to flow back and forth. Okay, so the salt bridge is for ions to migrate. What that does is it neutralizes the charges that are happening in each of the charges that are being generated in each of the containers, which we'll get into. In each of the half cells, you're going to have solutions. Okay, so I'm going to just do a classic example. This is going to be a zinc solution. So we'll say that this is zinc sulfate solution. The important part is the zinc part. So this would be positive 2 zinc ions. In the other half cell, we're going to have a copper 2 sulfate solution. and the important part is going to be the copper, positive 2 ions. We also need to have metal electrodes. So in the zinc sulfate half cell, we're going to have a strip of zinc metal. So solid piece of zinc, silver colored metal. And in the copper 2 sulfate half cell, we're going to have a strip of just shiny copper metal. Okay? These two things are your electrodes. So I'm just going to write it in blue because I drew it in blue. So those would be metal strips. And you're going to have one of them is going to be the anode, and one of them is going to be the cathode. You may have heard those words before. I'm not really sure, maybe in earth science or some sort of like physical science class, anode and cathode. The anode is going to be the site of oxidation. Always. It doesn't matter what kind of electrochemical cell you're dealing with. The anode is oxidation. The way you're going to remember that is anox. I think I mentioned this as a comment in that earlier video. Anox. And again, what is oxidation? Oxidation is the loss of electrons. The cathode is the site of reduction. So the way you're going to remember that is red cat. And what is reduction? It's the gain of electrons. So how do I know which of these sides is the anode and which side is the cathode? You can't just be like, I'm just going to pick one. It has to do with which of the elements has the greater draw for the electrons, which one has a stronger pull. So the way that you can find this very simply is on your reference table. Your reference table J, that activity series, the way that you figure out which metal is more easily oxidized is the metal that's higher up on the activity series. So let me just make a note of that. So again, table J, the metals side, the higher metal is more easily oxidized so it's the anode. And the one that's further down is less easily oxidized / more easily reduced. It has a greater pull on electrons, so it would be the cathode. Okay, so looking at your activity series, table J, and looking at the zinc and the copper, which metal is higher up on table J and therefore more easily oxidized, thus being the anode? Well, that would be the zinc. So we will just label this side as anode. So we know that oxidation is going to happen here. And we will label this side cathode, and the reduction will happen here. Now, we need the electrons to move from the anode to the cathode because the anode is the loss of electrons and the cathode is the gain of electrons. But where are the electrons going to travel? Well, what does electricity flow through in your house? Electricity moves through wires. So we need a wire. I'll just throw a switch on here. We need a wire to connect the metals to each other. So you could just like clip them on, like you'd have like an alligator clip or something on each of the metals, and you would run a wire from one to the other. You could put a voltmeter in the center here. Sometimes like on a Regents diagram, you'll see a little box with a V that's going to read what exact voltage of electricity is going to be generated. You might see a light bulb, because if you hook this up properly, you're making a battery, so it could run a light bulb, like a little LED. So something else you need to be able to do once you've labeled the anode and the cathode is to indicate the direction of the electron flow. So because of the definitions of oxidation and reduction, and oxidation is the loss of electrons, the electrons would travel from the anode to the cathode through the wire. Move from anode to cathode through the wire. Okay, so that's your complete drawing. Now, what is actually going on here that at the particle level? Okay, so what's happening at the anode, let's focus on that first. The zinc metal is going to lose electrons. So the process of oxidation here, the zinc metal will lose 2 electrons and become a +2 zinc ion. That's the oxidation half reaction. Okay, so the zinc, that's the strip, loses electrons which go through the wire, and it produces these zinc ions. Now, where do I already have zinc +2 ions? I already have zinc +2 ions in the solution. So what's going to happen is the ions that are produced through the oxidation process, so the electrons leave and pass up through the wire, the ions that are produced as the other product of this half reaction are going to go into, this solution. So I'm putting more positive ions into the solution than there were before. Well, what's going to happen to the actual size of my zinc strip as these atoms start breaking apart? The size of my zinc strip is actually going to shrink. It's going to get smaller over time because the atoms, the solid zinc atoms that make up the strip, are breaking apart. The electrons are passing through the wire, the ions are passing into the solution. Now, another thing that's happening here is we're screwing up our charge balance in our solution. We used to have nice even numbers of positives and negatives here, but now I've put more positives into the solution because of the addition of those zinc ions as a result of oxidation. Well, I got to neutralize positives. So what neutralizes a positive? A negative ion. Where do I find negative ions? In my salt bridge. Okay, so in this salt bridge, let's say we had a potassium nitrate solution that we soaked this in. The negative ions will travel into the anode. The anions, which are negative, travel into the anode compartment to help to cancel out those extra positives that were put in. I know this is a lot to take in, okay? So, take your time through this. Use some of those other resources as well. So that's what's happening at the anode. The metal that makes up the strip is oxidizing. Its electrons are passing through the wire. The ions that form as a result of the oxidation will fall into the solution. And we want to neutralize them by moving ions through the salt bridge. This all happens spontaneously. Now, what's going on the other side over here? So those electrons that had left the zinc strip have traveled over to the copper strip. So now I have all these extra electrons sitting on this copper strip. Well, those negative electrons are going to pull something positive toward them. So what do I have in this container that is positively charged? I have copper ions that are positively charged. So the copper ions are going to migrate toward the copper strip. So the copper ions that were in the solution will join up with the electrons that had traveled over. So this was from the solution. These came from the wire, from the anode. And when I add 2 electrons to a +2 ion, I end up with an atom of no charge, the same type of atom that makes up my strip. So those solid atoms that form are going to stick to the strip of copper. So this strip, this cathode, will actually get larger over time because atoms are accumulating on it. Now, in terms of charges, though, I've taken positive ions out of my solution. leaving an excess of negative ions. So I need to replenish the positive ions using ions from the salt bridge. So positive ions from the salt bridge move here. Okay, I highly recommend looking at the Voltaic cell video that I have in the link section, the Tyler DeWitt one. He has lots of little manipulatives that he uses here. So let me go on to the next slide and kind of summarize all of this stuff. Okay, so the two half cells, each half of the redox reaction takes place in a separate container. The two containers or half cells are connected by a salt bridge. So the job of the salt bridge is to allow ions to move but doesn't mix the solutions together. So you need to know salt bridges for ions, not electrons. The wire is for electrons. The electrodes that we have are metal strips. The anode is where oxidation occurs, so you just remember anox. And the cathode is where reduction occurs, and that's red cat. You also have to keep in mind the whole idea of Leo and Ger to know which direction the electrons are moving. They're moving away from the thing being oxidized to the thing that's being reduced. Salt bridge, we talked about that. There's a switch that will either close the circuit or open the circuit. The wire you need for the electrons from the anode to the cathode. The voltmeter will just measure the strength of the voltage, because if you, depending on the metals that you use, like zinc and copper will give you like 1.1 volts. It's like, there's tables you could use to figure this out. You don't have to know how to do that. But depending on the metals you use, you can maximize your voltage. You could use different combinations of metals that would give you different voltages. You could use different concentrations of solutions that would give you different voltages as well. And then the solutions in the half cells you need too. What else do you know? Okay, so the anode is negatively charged, the cathode is positively charged. So think there's a T in cat, and that's a positive side, and N for negative. I don't know. Usually I tell my classes voltaic anode negative spells van, something like that. So the electrons flow from the anode to the cathode. Because of the processes that occur at each cell, the spontaneous flow produces electricity. I also have a video linked in the content library section on how to make a lemon battery. You might have seen that or tried that as like a science project when you were in elementary school. This is a Regents diagram, basically the same thing that I drew. It has all the parts here. This one uses lead and zinc, and it also gives you the equation here. So you could use reference table J and look up lead and zinc and see where they are in relation to one another, and you could tell who the anode and the cathode are. So if you did that and you were like, okay, let me look up lead and zinc, you would see that the zinc is higher up, which means the zinc is going to be oxidized. So this zinc is going to be oxidized, it's going to lose electrons, and that means that the lead is going to have to gain electrons. So the electrons are actually going to move from right to left in this diagram, from the anode to the cathode. But the other thing is, in this particular diagram, they give you the equation. So you could just look at the equation and see who's doing what. So the lead is going from a +2 to a 0. So that's going down in charge. So that's being reduced. And the zinc is going from a 0 to a +2, and that's going up in charge. So it's being oxidized. So that matches up with what we said. Okay, so if the equation is given, you don't have to use table J. If the equation is not given, you'd have to use table J to figure out who the anode and the cathode are and which way the electrons are moving. Okay, so I just talked about this. When you're given a voltaic cell, how do you know which metal electrode is the anode and which is the cathode? The metal higher on table J will be the anode, and it will lose electrons because it is more easily oxidized than the other metal. All of chemistry, all of metabolism is all battling for electrons, like which has a greater affinity for them than something else. That's what chemical reactions are. It's a fight for electrons. And look, we just spent a whole year talking about it. Holy moly. Here's just like a little summary. In this reaction, is the zinc oxidized or reduced? It's oxidized. In this reaction, what is reduced? Copper ions, copper, zinc, or the zinc atom. So we have these two processes happening. So what's being reduced? Well, the copper is being reduced, and you always pick the reactant version. Which one has a stronger tendency to lose electrons? That would be the zinc, because we just said it was being oxidized. What's responsible for the conduction of electricity in the solution? The presence of electrolytes. That's your the ionic compounds. And the salt bridges the path for what to move? Ions. So the best, the easiest example is just a regular battery. You pop the batteries out of your TV remote, your little AA, AAA batteries, whatever. Those are voltaic cells. A car battery is a rechargeable voltaic cell. Your phone battery is a rechargeable voltaic cell. It's usually a lithium ion battery or a nickel cadmium battery. So the idea is that when a battery dies, it's because the anode has been used up. All of the anode has been oxidized and it doesn't work anymore and it goes dead. It can no longer supply the voltage that it was supposed to supply. So that's why batteries have expiration dates. Usually it's like years from when you buy it, because the chemical reactions, the battery is going to discharge very slowly on its own. It just hustles along when you actually use the battery. So when you have a rechargeable battery, the anode starts to deplete as you use your device. When you recharge it, you are reversing the flow of electrons and you're restoring the anode to what it once was. So different devices require different quantities of batteries because each battery gives you a certain voltage. And if you want to have a greater voltage to power your device, you need to use more batteries to do that. When I was a kid, when I was little, like the coolest present that I got when I was like 8 years old is I got a Walkman. And you are young and small children, but a Walkman was like, a portable cassette player, little audio cassettes. I thought I was the coolest, and I got these cool cassette tapes of like New Kids on the Block and Paula Abdul and Debbie Gibson because I was a pop music rat when I was a child. And when I first put fresh batteries into that thing, it gave more voltage than was needed to run the device. So when I would play my cassettes on a fresh set of batteries, the cassette would go so fast, it sounded like it was the Chipmunks singing. But then as the batteries would wear out, because I would just listen to it all the time, it would slow down because it wasn't giving enough voltage to juice the cassette. So isn't that an adorable story from my youth? How cute. So that's the idea. That's what a battery is. I really, really recommend you took your time through this, go back and rewatch parts of it. I know it's complicated. You don't just want to dive right into the castle learning. I want you to get a nice understanding of this. Check out a couple of the videos that I have linked. I think there's one voltaic cell one, and then there's a lemon battery, just if you wanted to mess around with that. And then I will make an electrolytic cell one for you for next week, and that will wind everything down. Let me know if you need anything.